Hello everyone and welcome to our lecture on sampling and aliasing. Today we will talk about sampling and what aliasing is, and then how to do anti-aliasing for image resizing. And finally, Richard Zhang of Adobe will talk about his recent paper on anti-aliasing inside neural networks. So let's first start by going into Matlab and see what aliasing means in images. I loaded our high frequency and low frequency images from our last lecture. Let's see and remember what they were. Okay, so now we will try to make these images smaller by taking every second pixel in each direction. Then it will be essentially half the size in both dimensions, both images. So you can see that when we look at the low frequency image, it still looks fine. But when we look at the high frequency image, it starts having these weird patterns. These are called the Moire patterns. And this is coming from aliasing, and this will only get worse as we make the image smaller and smaller. And this is because we simply cannot fit the high frequency details in less number of pixels. Until now, we talked about frequency domain in the analog term or the continuous domain term. But in images, in digital signal processing in general, we are looking at samples of images because we have a discrete representation. In images, these samples represent each pixel. So we have seen that if we have a signal like this, for example, in the frequency domain representation, if we look at the magnitude of the frequency response, we will see something like this. It will be symmetric in the frequency domain because the negative frequencies and positive frequencies represent more or less the same thing for us. And if the input signal is real valued or it is not complex valued, like any normal images that we see in real life, we will get a symmetric frequency response like this. But when we want to go from this analog representation to a digital one, then we need to take some samples. So, for example, the digital version of this signal would look like this. There are some discrete samples taken from the signal, and that's what the computer would see. And how we model this sampling process is through an impulse train. So we will have a series of impulse functions. These are infinitesimally small width samples with very high values, and the characteristic of a single impulse is that if you take the integral of this function from here to here, it will give you 1. And the frequency domain representation or the Fourier transform of this impulse train also looks like an impulse train. And the period of this impulse train will become the frequency difference between these impulses that appear in the frequency domain. and we will sample this signal using this impulse train by multiplying it in the spatial domain, which would mean convolution in the frequency domain. So after we multiply this signal, the sample signal will look like this, as a discrete set of samples. But in the frequency domain, something more interesting will happen. Multiplication in the spatial domain corresponds to convolution in the frequency domain from our convolution theorem. We also know that is like filtering an image with a filter that has just one in the very middle, and that's it. And for an impulse that is a bit away from the 0 point here, it will be like convolving an image with a filter that only has one value outside the center. And we have already seen in our filtering lecture that this convolution results in a shifted version of the original signal. So convolving this image with this impulse will give you a copy of it, just shifted a little bit. And as we have more impulses in both domains, infinitely many, these will also repeat itself infinitely many. So when we sample the signal, we are actually replicating it over and over again in the frequency domain. This is how the frequency domain of a sample signal looks like, just a repetition of the original sample signal. You might be confused about what I am trying to show in this frequency domain. This is just a very simple made-up frequency domain response for a signal like this that has a mostly low frequency component, so it's not changing very quickly. We can also plot a very simple high frequency signal that would maybe behave a bit more crazily. And then if we also make up a frequency domain response for this signal, we can expect that it will have more higher frequencies, should be symmetric, and the other one. And this will start creating trouble when we sample these signals and start repeating these frequency domains in next to each other. So before, what we did was take some samples from this one, and we saw that it repeated itself like this. But if we take the same number of samples, then the samples will start not being able to represent all the changes inside the signal. As you can see, if I am to connect these dots, I can more or less reconstruct the signal. But if I am to connect these dots, then I will be missing a lot of details that are coming from very quick deviations in the signal when it has high frequency components. That's how we define high frequencies anyway. And when we take the same rate of samples from a more high frequency signal, it will still repeat itself in the same way, but just repeating it the same way will we will see that some of the higher frequencies, when the frequency domain is repeated too quickly, will start adding on top of each other. And when we compute the frequency response of this sample signal, then it will look like this, because we add these up. So some of the frequency information or the higher frequencies are not realistic when we take this type of this number of samples from this signal. The frequency domain representation of this signal starts colliding with each other, and when we take the samples, then the signal in the end is corrupted, and this is called aliasing. This is what we mean by aliasing. When we try to sample a signal with less number of samples than it requires, then the resulting sample signal will have problems called aliasing. And there are different ways to address this. Let's look at them. Now, we saw that when we take a little number of samples from a complex signal, like only the red ones over here, this repeats itself very quickly. So it starts colliding on itself. If we take more number of samples, since this distance t will be smaller, the distance between the impulse responses in the frequency domain will be further away from each other. So the repetition will be a bit better. And when we actually look at the final sample signal, it will not have this issue anymore. So by taking more samples, we can get rid of aliasing. But this is not always the perfect solution, because more samples mean more data or better sensors or more file size. So if we want a smaller image, for example, of a complex scene, we need to somehow get rid of the high frequencies with a low pass filter. For example, if we filter this signal with a low pass filter, the resulting frequency domain will be like this. And when it is like that, when we repeat this signal with a smaller sampling frequency, it will stop colliding on top of each other. And this is called anti-aliasing. Anti-aliasing is as simple as applying a low-pass filter before sampling or resampling a signal. And the sampling rate, the minimum sampling rate, is called the Nyquist sampling rate, and it is 2 times the maximum frequency that we have in the image. Because when it is 2 times the frequency, they will be just far away from each other, enough not to collide with each other. And this is called the Nyquist sampling theorem. Let's see how anti-aliasing works in Matlab. We can have a look at the frequency responses of these to check. Actually, let's do this. And let's look at the frequency responses of the original high frequency image and the downsampled high frequency image. Okay, so in our original signal, we see that there are high frequency components, but when we make it smaller, you will realize that these high frequency components are now corrupted because they collided with each other. And when we do the same thing for the low pass image, it will not look as bad. So since this image didn't have many values outside this region to begin with, when we make it smaller, we are still able to fit it nicely, and the shape doesn't really change when we make it smaller because the aliasing hasn't started happening yet. But we can fix aliasing in the high frequency image by simply anti-aliasing it with a Gaussian filter. So let's first create our filtered image. I am cheating a little bit and using the imgauss filter function. Let's do sampling. And let's look at our frequency responses again. This is the high frequency sampled, high frequency filtered, sampled. As you can see, when we filtered it beforehand, we got rid of some of these overlapping high frequency details, so that when we look at the result, it will show less aliasing in the end. As it is painfully obvious, as you can see here. And this is called anti-aliasing. We do quite a bit of downsizing or downsampling in neural networks, for example in max pooling layers. But when we talked about neural networks, we did not talk about anti-aliasing. So today, Richard Zhang will join us about his recent paper on anti-aliasing inside networks. Richard is a research scientist at Adobe Research, interested in computer vision, deep learning, machine learning, and graphics. He got his PhD in 2018 from UC Berkeley, advised by Alyosha Efros. And before that, he got his master's and bachelor degrees in ECE from Cornell University. So let's hear from him what is the deal with anti-aliasing inside neural networks. Thank you very much, Richard, for joining our lecture today. So I will leave the stage to you.
My pleasure. Thanks so much for the invitation. So this is a paper I published in ICML last year. So let me show you a curious kind of phenomenon in deep networks. These two images here are classified correctly, but these two are not. And the only difference between these is a seemingly innocuous shift operation. And what we see is that deep networks are in fact not shift invariant. If we take the image and simply slide it around by a single pixel, we see classifications really jump around a lot, and we even see oscillatory behaviors. So what is actually happening here? Well, we have to investigate why shift invariance is being lost. After all, underneath the hood, we see that there are a few components. For example, convolutions are shift equivariant. That means the features should be sliding around with the image. And pooling is supposed to build up shift invariance, giving you a bit of spatial slack. Now, if this were the whole story, then we should not actually see the behavior we saw on the previous slides. The deep network should in fact actually be shift invariant. But it turns out this is not the full story. And that's because of a concept that you just recently learned in class, which is aliasing. So how does aliasing come in? Well, there's this factor, this parameter called stride. Now, striding can be in both convolutional layers as well as pooling layers. But in essence, striding is a subsampling operation, a naive subsampling operation that ignores the Nyquist sampling theorem and introduces aliasing into the system. So a quick review, we see that if we're undersampled, for example, we have these red samples on this high frequency blue curve, we see that this is not meeting the Nyquist sampling criterion. And what it's causing is a misrepresentation of the underlying signal. If I gave you these red dots, you would maybe connect the dots and get a very different idea of what the actual underlying signal is. And this is not good. For example, we could see it in rendering. This is kind of a classic example. As we move further from the camera, the sampling rate is decreased, and we see this weird phenomenon that the further squares appear bigger than the closer squares, which is a misrepresentation of the underlying checkerboard signal, and that's not good. Okay, so how do we fix it? Well, the only surefire way to fix it is that you just never downsample, right? You just never have a sampling rate that's too low, and you just never downsample, but that's going to be computationally infeasible. If you try to keep a feature map that's the same spatial size as your image, you're going to run out of GPU memory almost instantly. So we do have to subsample or downsample by some factor. So what are we going to do? Well, if we just naively subsample, the high frequencies are going to be misrepresented, as we saw in the previous slides, right? So that's what we're showing here. A signal coming in, you take every nth sample, you're going to get an alias signal coming out. That's not good. But as we've seen, the fix is that before subsampling, we need to anti-alias by blurring, okay? So by low-pass filtering, we're essentially removing the frequencies that are too high to represent on the output. So we're just going to not represent them at all rather than misrepresent them, okay? And now you see this through a lot of different names. For example, blurring, pre-filtering, anti-aliasing, and low-pass filtering. They're all kind of the same concept. And if we see that, we get something that looks a lot better here on the right with the pre-filtering. Okay, so what does aliasing have to do with loss of kind of shift equivariance or these instabilities that we're seeing? Well, here, we'll just take a simple kind of demonstration. On the left, we have an image of this man with the camera. We're going to take him and shift him to the right, and then we're going to downsample that image. And if we do it naively, you see that things kind of flicker in and out, whereas if you add pre-filtering, the output is much more stable. So this is just a simple downsampling operation, which is a linear operation. But we can see that and imagine that in deep nets, even though it's nonlinear, we have kind of similar effects going on. And this may be why we're seeing these instabilities in this first example. Okay, so why is anti-aliasing not used in deep nets already? Well, it turns out it used to be in average pooling. So in Linnet 1989, average pooling is a box filter, and it's doing some anti-aliasing. Now, we know that you're supposed to anti-alias in signal processing and image processing and graphics. And in computer vision, you can look at section 2.3.1 of the Slitzky book, and that concept is in there as well. So what happened in deep learning? Well, it turns out max pooling through very systematic operations or evaluations ends up getting better accuracy. So at around 2010, a decade ago, the decision was made to kind of forego anti-aliasing and abandon it in favor of max pooling, which is supposed to give you better accuracy. Okay, so what happens here? Well, let's maybe max pool a simple signal together, 0, 0, 1, 1, 0, 0, 1, 1. If we max pool 0 and 0, it's 0. Max pool 1 and 1, it's 1, and we get this result. And if we take this input signal and shift it by a single index, we would max pool 0 and 1, which is 1, 1 and 0, which is 1, and so on and so forth. And we'll get this result. So what we see here is that we're actually not getting shift invariance at all. What we're seeing is that max pooling is straight up breaking shift equivariance. Simply by shifting the signal by a single index, we get dramatically different answers. Okay, so I can show you this in a kind of more realistic scenario as well. So this is a classification test bed. So this is a CFAR classification test. We're going to use a VGG network, which has 5 max pools. It goes from pixels, which is 32 by 32, to a classification, which is 1 by 1 with no spatial extent. We're going to downsample the feature map by a factor of 2 through 5 max pool operations. And what this allows us to do is probe the internals of the network to see how shift equivariant each of the internal layers are. If something is shift equivariant, it means that you can take the image X, you can shift it and extract features, or you can do it in the other direction. You can extract features and shift the feature map. And that is, these operations should be commutable. And we can check how close to this shift equivariance condition each of the internal layers of the network is. Okay, now there's one kind of detail we have to take care of. If you shift an image or feature map, by necessity, you're going to delete pixels on one side and have to make up pixels on the other side. And so if you don't take care of this properly, you're going to deviate from the shift equivariance condition, and it's only going to be because of edge artifacts. And we're looking to try to isolate the effects of aliasing here. So we're going to use this trick from image processing or signal processing, which is the circular convolution and circular shift, which means that any deviation from the shift equivariance condition won't be due to any edge artifacts. It'll purely be due to the downsampling operation. Okay, so now let's just probe each of the layers. So in Conv1, what I'm showing is for different amounts of shifts, vertical and horizontal, how far it deviates from the shift equivariance condition. And all blue actually just means 0, that equality is holding, and we have perfect shift equivariance. And that makes sense. You're doing convolution, you're running a sliding window function across the whole image. That shouldn't create any problems for you at all. However, if we go to the first pooling layer, we see this interesting stippling pattern occur. And what this means is that for an image, if we shift it over by a single pixel, we'll get a completely different representation of it in the first pooling layer. But if we shift it by an even number of pixels, we'll then recover that representation. So imagine this. You have a video of a still scene with an object kind of moving to the side, 1 pixel at a time. What that means is that for every other frame, you're going to get a different representation. Then it's going to move another pixel and you'll get your representation back. And this is probably not a behavior you want. You don't want 2 representations of the exact same underlying pixels. But this is actually what we're getting just because of the way that we're building our networks. Okay. And so we see that as we go through the network, every time we hit one of these pooling layers, which is striding by a factor of 2, we're doubling the periodicity of this stippling pattern, and it just gets kind of worse and worse and worse through the net. Okay, so our goal here is to reconcile the classic anti-aliasing that we know is kind of more stable with max pooling, which is kind of this more modern way that this modern tool that was used in deep nets. And to do that, we just have to make one simple connection, which is that max pooling underneath the hood is equivalent to 2 operations done sequentially. So here's an example of max pooling. You take a 2x2 block, you take the max value, and you copy it to the output. Then you go to the next 2x2 block, and so on and so forth. This is actually equivalent to doing max, but at every single spatial location, so densely, and then taking this intermediate feature map at taking every other value. Now, the key to this interpretation, well, the left and the right here are functionally equivalent, but the key is that by kind of factoring it into these 2 operations, we see that the problem is in the second operation, the subsampling operation. That's where the shift equivariance is being lost. That's where the instabilities are coming in. And based on our kind of signal processing principles, we know exactly how to fix it, right? So we can copy the first operation, that's fine. We just need to add an anti-aliasing filter before the subsampling. Now, these 2 operations, the blur and the subsample, can be evaluated together. So really, in the end, this is our anti-alias version of max pooling. So instead of 1 line of code, I'm just asking you to add a second line of code. And now we're kind of much more stable. Okay, so here's just an example on our toy signal. We do max densely. Then we can low pass filter it. And then you see that whether you're in one spatial location, the kind of green position, or the pink location, they're not exactly equal, but now you're much more stable than before, simply by doing this little blur operation. Okay? And we see that indeed in our CFAR example, we're much more stable as well. So this is before, which is you see a lot of red, and after, it's much more stable. Before and after. Okay, now I've used max pooling as an example, but you might know that max pooling is actually going out of style in some sense. But for example, strided convolution is a way that many networks do downsampling now. But the cool thing is that we can note that all the problems and actually the fix kind of holds between the max pooling and convolution operation, right? So we can take convolution, stride 2, which is also aliased, but we can fix it by making it stride 1 instead, and then adding our blur pool layer after that. And that means we can just anti-alias FresNet instead of VG or AlexNet. Or we can take average pool and add a better kind of blur kernel, and that improves those networks at all. And so the takeaway here is that we can take any previous off-the-shelf network, which has this essentially this bug in it, aliasing, which is a bug, and we can go ahead and create an anti-alias version of it very, very easily, just by this simple drop-in replacement. Okay, so let's look at some results. So this is on ImageNet, which is a large-scale classification test. On the y-axis, I'll plot consistency or shift invariance. This is how often two shifts of the same image are classified the same. It's not actually looking at if they're correct, it's just checking for consistency. Now we do care if something is correct or not, so we plot that on the x-axis. And here are a whole bunch of networks in this space. Okay, so up and to the right is good. Now my expectation was that when adding anti-aliasing, we would perhaps move up and to the left because we're often dealing with trade-offs, right? I thought maybe to get some consistency, we would have to sacrifice some accuracy. But to my surprise, the first network I ran, we actually saw improvements, and I ran it across all the networks and I saw improvements in both factors, okay? So what this is indicating is that if we were to adhere to kind of basic signal processing principles in the beginning, we would not only have gotten better consistency in these classic networks, we also would have gotten better accuracy as well. Okay, so here are some kind of qualitative examples. On the left, you see the baseline. On the right bar, you see the anti-alias version, which is kind of much more stable than before for some of these selected examples. So these are kind of fun to look at. Okay, so in summary, we've seen that striding aliases, because striding is exactly equivalent to the subsampling operation. But luckily, we've learned about anti-aliasing, and we can actually use that tool in deep networks as well, right? It was developed in signal processing, but it turns out deep features on images are also signals, so we can adhere to those signal processing principles and use the appropriate bug fix. And what we've seen is that we get better consistency to shifts as well as accuracy. We also get some nice properties out for free. For example, stability to perturbation. So if I were to rotate the image, we would also be more stable to that. And we would also be more stable to robustness to corruptions. For example, if I were to add Gaussian noise, we would see smaller fluctuations there as well, kind of just for free. Okay, so code and models are online, and it's a kind of simple replacement, and you can actually kind of pip install the models now. Okay. Yeah, that's the pip install code right there. Okay, thanks a lot.
Thank you very much for this very nice introduction to how to anti-alias deep learning networks. But I know that you do a lot of interesting work in computer vision and kind of computational photography. Would you like to give us an overview of what kind of things you do at Adobe?
Of course, yes. So a lot of the research I'm engaged in is looking at using deep networks for image synthesis. So some of this stems from my work in graduate school. For example, kind of one of the first projects I worked on was image colorization. So you can take color images scraped from Google, you can desaturate them so they're black and white, and then you can predict the color components from the black and white components. And so this was one project I did in grad school. Then I added some kind of user interaction as well, because it's kind of inherently multimodal, right? If I have an image and a person's wearing a shirt, we don't know if it's blue or red, but we can add some kind of user guidance to add color to that as well. So this work is now kind of a feature in Photoshop Elements as well. So it's kind of interesting and fun to see some work I did in grad school go ahead and be used in products as well. Yeah, and so from there, I'm looking at more kind of general image-to-image translation problems as well. So we have some recent work on disentanglement of structure and style. So just learning from a collection of images, for example, a whole bunch of landscape images or a whole bunch of churches, you discover natural factors of variation that's also gives you a tool that's amenable to image editing. So in the end of the day, I would like to, maybe I took a picture of a nice landscape image, but I want to make some modifications. I want to add some snow. I want to maybe change the clouds a bit. How do we create a model to do that? And then finally, I'm also looking at some
unsupervised learning for that, right? Or
exactly, yeah. Yeah, unsupervised, kind of a self-supervised approach, yeah. But really, we just want to deal with kind of different levels of supervision. So sometimes you're given domain labels where you have a collection of snowy images, a collection of rainy images, a collection of sunny images. Other times you're just given a whole collection of images and you'd like to discover the factors of variation there. So that, in essence, is kind of a disentanglement problem, right? You want to get the textures or the style kind of separated from the structure. Yeah.
Thank you very much for joining us. I hope we will get to see you again.
Yeah, thanks so much for having me.
If you want to check out more of Richard's work, his website is linked in the video description. We do not have a required reading part for this particular lecture. If you want to learn more about anti-aliasing in neural networks, you can check out Richard's paper as further reading. Thank you very much for joining us today, and I will see you in our next lecture on interest point detection.